Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center at the University of Colorado, Denver. Today we're going to be solving a problem using circular motion, a car driving at a banked angle on a circular track. So let's get started. Physics checklist is here to kind of follow through. Won't be there every time, but it's there for us to follow today. First thing we want to do is read the question. All right, so a car is driving on a banked circular track with a radius of 50 meters and at a speed of 25 meters per second. What angle is the track banked? So we're looking for the angle the track's banked. I think that's really straightforward. There's nothing we need to say about that, and I think we all know what they're looking for here. All right, so theta, right? So given. Looking for givens here, which is just writing down what we know about the problems. We were given the velocity, meters per second. We know because of the units, right? It was an omega. It would have been radians, right? So we know that this was given to us in velocity, and in terms of circular motion, that would be our tangential velocity. We know our radius, which is 50 meters, right? We're looking for the angle. We know G. I didn't know to write it in there, so I wrote it in there at the end. But yeah, we also know G, and that's all we know. All right, Freebody diagram. Okay, so here this gets a little tricky, right? I want you to really understand this Freebody diagram because this is the essence. This is the important part of this question, I think. Solving it is pretty straightforward, I'll be honest with you. But the Freebody diagram is what's important. So we have a lot of forces going on based on what's going on. We have forces that are making us, that are keeping us, maintaining us, right, moving in a circle. And we have forces that are maintaining us or balancing us here on the track, right? So which ones do we use? How do we know what to use, right? Well, we know for circular motion, right? If we're looking for circular motion in terms of what's going on, we could totally, or what we need to do, the concept we need to apply, I apologize about that, is that we're looking for a force towards the center of our motion, right? Anytime we're moving in a circle, there's always going to be some sort of net force towards the center of our motion, whichever way we're turning, right? We know that, right? So we're looking for the force towards the center of our motion, right? So that's a good way to decipher what the heck, what forces you're looking for, right? Again, based off what we were given. Could we do some other things here? Maybe, but that's not quite what we're wanting to look at here. So, all right, so we want to look at it as such, right? So, and what we know, what I'm trying to say, is that mg sine theta, what we were given at the beginning of the semester, right? We were drawing free body diagrams on boxes. We would do the weight and normal force. We'd break mg up into its components, right? Mg cosine theta is balancing out the normal force. Mg sine theta is going down the ramp, right? If there's ever a force opposing it, right? Like friction, it will go up the ramp. Things like this. Unless, right, if we're being pushed up the ramp, mg sine theta will stay consistent. Friction will change direction. I'm not trying to get into that right now. But we know these are the forces that are going up and down the ramp. But what aren't they? They're not pointed towards our center of motion, right? These are pointing down the track, up the track, but we need something that's towards the center of our motion this way, not down the track or up the track. So that's why we don't look at mg sine theta or cosine theta. Those aren't describing our force towards the center of motion, right? And we know that we need that because what we were given, radius, tangential velocity, we want to use what we know about circular motion to find the angle of this banked track, right? All right, so what we can see is that it's that normal force, one of the components of the normal force, that's actually the thing pointing towards the center of our motion. I notice that I don't have AR there, but that should be pointing in the same direction, right? So not mg sine theta, not mg cosine, n sine theta is the force pointing towards the center of our motion here when we're at a banked curve. All the time, that's what it's going to be. Okay, so you should get to know this free body diagram, know how to draw it, know why we're drawing the things that we're drawing and what we're saying when we're saying. Okay, so the normal force is that force towards the center of our motion, this n sine theta. This n cosine theta here is what's balancing out mg. So look at this, mg cosine theta, right? This component of weight is going to balance out the normal force, or n cosine theta is going to balance out the whole component of mg. We can look at this two different ways. We can do that with a lot of things. Things that are on a rope swinging. We can look at the tension and the components of the tension, or we can look at mg and the components of that. Depends on what's going on. So that's what's happening here, all right? So we want the force towards the center of our motion. We know that's n sine theta, right? And so that's why we break the top part up into its components. I have everything drawn out here for you, but if we're just looking to solve for circular motion, just want to use that, we don't need this bottom part. We need just that top part. That's the free body diagram that we want, right, with our purple forces there and the blue. We don't need any of the green here, okay? And as you can see, I have these colors here matching up with our coordinate system. So these circled in green are matching our coordinate system in terms of the banked angle. These circled in blue are matching our coordinate system based off of this our normal force coordinate, our normal force components, okay? So also notice that, because we have two different coordinate systems here. There's one on the angle of the curve, and then there's one there's one in terms of the components of mg, and there's one in terms of the components of the normal force, however you want to look at it. But I circled them in the appropriate color that's matching. So the green's matching mg, blue's matching the normal force. Okay, so these are our forces that we have. So we break the normal force, again, the blue, into components to find our force towards the center of motion. If we were asked why this thing's balanced at the center, what are the forces associated with balancing this in the center of the track, we would look at these. Okay, so again, that's why we're doing what we're doing. You could draw this, so this is a full free body diagram. This is everything that's going on this car, okay? But if we're just looking for the bank curve, we don't need the green. Your professor doesn't need the green. They're not gonna draw the green in class. You might ask, well, what happened to the green pieces on here, these components? Because we've been drawing them since the beginning of the semester. We're not looking at that part of the problem. So we don't need to look at them. Are they there? Yes, they're there. They're 100% there. Okay, they don't go away. It's just we want the force towards the center of the motion, so we want to break that. We know that force, that component of the normal force, is what's pointing towards the center of the motion. So that's the components that we want from this problem. Okay, that's why we did this the way we did. Understand that, rewind that, understand why we did what we did here. Because the free body diagram is everything here. Everything, all right? Okay, so the concepts associated with circular motion, we know are Newton's second law, right? We might also have Newton's first law going on as well, based off what's going on in our free body diagram. We know definitely that Newton's law is what we want to look at because we were given forces, right? We weren't given anything else. We were just given forces, so Newton's law is how we want to look at these things, okay? That's very, very, very important to understand. Okay, so what we want to do is follow our physics checklist and write down the equation that goes with those concepts. So we know in the x direction, right? And again, this blue's our x, not the green. The blue's our x. We have a net force, right? That's what's making us move in a circle. So Newton's second law is going to apply to that x direction. The y direction, right? This car's still balanced on the track. It's not floating off or breaking through. So this y direction, right here, is going to be balanced. It's in equilibrium, right? And you want to write it as such. And the next thing we want to do is fill in our equation from our free body diagram. So we know in the x direction, there's n sine theta, right? We know it's there. Are there any other forces in the x direction in terms of the blue? We're not looking, the green is essentially, we're not looking at that part. And there's not, that's the only one. So you write n sine theta, there's no other forces, so now you can make it equal to MAR. I see a lot of students uncomfortable with this, and don't be. You can have just one thing over here, that's okay, and then end the equation. Don't be worried about that, that's A-okay. All right, we're just, as long as it matches your free body diagram, that's what's important. All right, so that's the only force, that's our net force, that's what we put there, equal to MAR. They both have positive signs because they're both pointing in the positive x direction. That's why they have the positive sign, right? Now, what we want to do is we want to turn that, because that's the radial acceleration we're looking at now. We know that the radial acceleration in terms of the tangential velocity, what we were given, is written the tangential velocity squared over the radius. So we want to change that to that equation, which again, we're just kind of putting things together at this point, step 7, and then we'll kind of stop there and move on to the y direction. Now, we said that equilibrium is going on in the y direction, right, in terms of this car being balanced on the track. That's why we wrote Newton's first law. Now, to fill in this side of Newton's first law, the forces, right? Just look at our free body diagram. We've got n cosine theta sticking straight up in the positive y direction. So that's going to be positive, n cosine theta, right? Then minus mg. Why is this negative? Because it's in the negative direction. Please keep that in mind. Okay, you have to know why these signs, where these signs are coming from. It's not magic, and why these equations are morphing the way they are. Okay, so it turns into what it is from our free body diagram. We take our forces from our free body diagram and fill this thing in, and then that's it. We just have mg and n cosine theta and the y in terms of our normal force, so we're done. That's it. Make it equal to 0. Now, we look at these. We know that we're looking for theta, right? We have tangential velocity, right? We notice that, right? We have the radius. We don't have mass, and we don't have the normal forces, what we notice. But we see down here that we can kind of solve for the normal force, right? We can kind of say, oh, we can solve for the normal force. I'll bring cosine theta, I'll bring mg over, right? And then cosine theta, I'll divide by that. And there we go. And you can replace that normal force with this mg1 cosine theta, which is what we did here, right? So you're going to get that sine theta is going to stay on top. That is going to turn into m1g, right? And then over cosine. Cosine's still going to be there, right? So again, we're putting this n. This n is coming up into here. It's going to replace that, and that's what we're doing, okay? And then you finish it off, m1vt squared over r, which is what we did here. Now, look at that. We didn't get mass. One thing I see is that students will read this question. They'll say, well, I didn't get mass. I can't do anything. What do I do? This problem's hard. Don't do that. Do what we did. I didn't even think about mass, okay? And don't. Work through the problem. Pretend like you have mass. See if something will happen. Maybe something will cancel. What do we see? Masses cancel. They're on each side, right? Each term. So these m1s are going to cancel. They're going to go away. And that sine theta over cosine theta is equal to tangent theta. Make sure you know that. Sine theta over cosine theta is equal to tangent theta. We know this, so we can turn it into tangent theta, right? And m1s are going to go away, so the masses are gone, right? Now we need that theta. So the first thing we need to do is divide by g, so now that g comes down there next to the r. Then you do the inverse of tangent, right? To get that theta, and you're done. So just bring tangent over in your calculator. You'll just do inverse of tangent, right? Make sure to put vt squared, right, over g times r. You have all those variables. Just put them in your calculator, and you're done. All right, so again, I want you to focus on the free body diagram here. This question's pretty easy to solve. Okay, so the thing to focus on here is why we're breaking up the free body diagram in the way that we are, and the appropriate forces, how we're applying them. All right, good job. Proud of you. Keep up the good work. If there is anything you may need, come down to the Learning Resources Center. We're here to help. Super proud of you. Keep up the good work, and I'll see you in the next one.